Welcome. Let's talk about how we measure the amount of energy that's being transferred in a chemical process, something known as calorimetry. Let's start with the idea of thermal equilibrium. So thermal equilibrium occurs when there is no net transfer of heat between two objects that are in contact with one another. And this happens when those materials are at the same temperature. So before thermal equilibrium is reached, energy is going to be transferred from a material with a higher temperature to a material with a lower temperature. So the question is, how can we measure that amount of energy that's being transferred? And one tool we need in order to accomplish this is this concept of heat capacity. So heat capacity has a symbol either uppercase or lowercase c depending on what the material is. But it's basically how much heat do you have to transfer in order to change the temperature of an object or a material by 1 degree Celsius. Not everything heats the same. You've probably experienced this in your everyday life. Things that are metal tend to heat up faster than something that has a lot of water in it. So this heat capacity gives us a relationship between the amount of energy where a lot of energy being needed to heat an object is going to cause it to heat more slowly, and so that's going to have a higher heat capacity. Where something with a low heat capacity, a little bit of energy will cause a large temperature change. The exact equation we're going to use that's going to connect heat capacity to the amount of energy that has been transferred depends on the form of the material we're looking at. So we're going to take a look at 3. So first, if we have an object, then the equation we're going to use is Q equals C delta T. In this case, Q is going to be that amount of heat, that energy that has been transferred. C is the heat capacity of my object. And then delta T is the change in temperature. And so this is going to be the final temperature minus the initial temperature. So please note that if the temperature goes down, that delta T is going to be a negative value because the temperature decreased. If the temperature increased, it's going to be a positive value. Unit-wise, we know that heat has units of joules, and that temperature, we're going to use units of degrees Celsius. In any equation, the units on the left side and the right side have to match. And the heat capacity has the units that make the left side and the right side match one another. And so in that case, that means I need to end up with joules. I need to have degrees Celsius cancel out. So my units are going to be joules per degree Celsius. If I have a material that's not a standalone object like a beaker or a thermos, instead I have a material that you can have different amounts of, then oftentimes it's easier to work with a mass of a particular material. And so the equation we'll use is Q equals mc delta T. And you should remember this one from first year chemistry. Here again, Q is heat. Now M is my mass, and we're going to use grams here. Delta T is still my change in temperature. And so this C is called my specific heat capacity. And in order to get all of my units to match left and right side, it needs to have units of joules per gram degree Celsius. The last connection between heat and specific heat capacity that we're going to look at is when you're talking about how many moles of a substance you have. And so this is called your molar heat capacity. Your equation is Q equals N for moles, C sub N to specify that this is the molar heat capacity, delta T. And in order here for the units to match left and right side, the units on your molar heat capacity need to be joules per mole degrees Celsius. Let's put some of these equations to use. So let's say I've got some water in a beaker, and I'm going to heat it up from 8.5 degrees Celsius to 74.60 degrees Celsius. If we want to calculate how much heat that process takes, we need to recognize that the heat has to go to 2 places. It has to heat up the beaker, and it has to heat up the water, which means that the total amount of heat required will be the sum. Well, the beaker is an object, and so the equation we're going to use to calculate the heat gained by that beaker is a capital C for the heat capacity of an object times the change in temperature that we're carrying out, while the amount of energy gained by the water will be the mass of the water, the specific heat capacity of the water, and then the change in temperature. Once we have that recognition, all we have to do is plug in our numbers. Note here that the change in temperature is this 74.60 minus 8.5 because we're doing final minus initial. And this is 66.10 degrees Celsius. And the same temperature, what change was experienced by the water. And so over here, I just put that temperature change in as is. Once we have those pieces, it's just a matter of plugging the numbers into the calculator and doing the math. So if we take a look at this answer, 1.3 times 10 to the 5th joules, you'll notice that's positive, which makes sense because we had to put energy in order to heat up the water, and so it is an endothermic process. Measuring the amount of heat gained by a material is useful, but often what we're going to want to do is have a chemical reaction occur and figure out how much heat it either absorbs or releases. It's really hard to measure chemicals reacting with one another. So we're going to use a technique called calorimetry, where we'll figure out how much energy is being released or gained by a chemical process by measuring it indirectly. So what are we going to do? Pretty much we're going to put it in water and let the heat either gained or lost by the reaction be transferred into or out of the water. And we can measure the water itself. And so the most common setup at this level, and what we're going to use, is a thermos or a coffee cup that we're going to fill with water. And then we're going to make sure this is fairly well insulated. So if we're using a coffee cup, we'll use a double coffee cup. If we have a nice thermos, to try to keep all of the heat that's being transferred inside the coffee cup. We don't want what's outside of our coffee cup to influence our results. We are going to stick a thermometer into that water so that we can monitor how the temperature change of the water changes, and then we'll have our chemicals and our chemical reaction occur within that water so we can measure what's going on in there. And what we are able to recognize is if this is what we've got going on, the heat that's being given off by the reaction or that's being absorbed by the reaction, depending on the situation, is going to go into both the water and the cup, hopefully just the inside of the cup, but the water and the cup. And so as a result, we can say that, okay, whatever that is, if the reaction gives off heat, the water is going to gain it. If the reaction gains heat, the water is going to lose it. They're going to have opposite signs. So mathematically, the value for the heat of the reaction, so for Q of that reaction, is going to be the opposite, got a negative sign, of the amount of energy that's being gained by the solution. And so I'm going to change from water to solution because we've now dissolved stuff in it. And the amount of energy that's going into the cup or into our calorimeter. We already have equations in order to calculate Q of solution and Q of our cup or our calorimeter. And so generally speaking, we'll use MC delta T to calculate Q of the solution. And then we're going to use the calorimeter constant times the change in temperature to calculate the amount of energy that's gained by the cup. We can just add those together to figure out the total energy change. I want to emphasize that whatever the energy change of the cup and the calorimeter is, it will be the opposite of the energy change of our chemical process. Let's take a look at one example together and see what we can do. So let's say I put 100 grams of water into my coffee cup, and I know the calorimeter constant of that cup. We're going to add 2.5 grams of lithium bromide, and we're going to see that temperature increase. So right off the bat, you know if the temperature increased, the cup and the calorimeter gained heat, and the reaction gave it off. So what I'm going to say is that the Q of my reaction, this is really a dissolution process. We can argue over whether it's a chemical reaction another day, but I'm going to call it a reaction right now, is going to be the opposite of the heat that's gained by the calorimeter and the heat that's gained by my solution. So by the water with now the lithium bromide dissolved in it. So substituting those equations that we know, we've got the calorimeter constant and the change in temperature to account for the energy gained by the calorimeter, and MC delta T to account for the energy gained by the solution. It's important to note that for most things that we're going to do, we're going to assume that our solution has the same specific heat capacity as water. Because when solutions are fairly dilute, that's a pretty good assumption. But since it's a solution, it's both the water and whatever we've dumped into it. And so our mass needs to include both the mass of the water and, in this case, the mass of our solid. So if something's dissolving in the water, you have to include its mass in this equation. Well, with all of that in place, let's go through and do the math here and plug the numbers in. So when we solve all the math, we find that the heat that was transferred in this process is a negative 1.4 times 10 to the times 10 to the third. And this is indicating that our reaction gave off heat, just like we said at the beginning. And so this is an exothermic process. Well, this is true for 2.5 grams of lithium bromide. That's the amount of heat for that small amount of lithium bromide. What if I wanted to scale it up? What if I wanted to know the amount of energy that would be transferred if an entire mole of lithium bromide were dissolved? Okay, so here's my question. How much heat would be generated when 1 mole of lithium bromide dissolves? The key here to recognize is that I can scale up the process. If 1.4 times 10 to the third joules of heat was given off for 2.5 grams, I'm going to have more energy being given off when I have a whole mole, which will weigh more than 2.5 grams. So let's figure out how many moles 2.5 grams of lithium bromide was. So what I had happen in the problem was that I had 1.40 times 10 to the third joules of energy given off when 0.0288 moles of the lithium bromide dissolved. I want to know how many joules are going to be generated or given off when I have 1 mole. Well, that's just a proportion, so we can just solve for x. And so what you're going to find is you have 4.87 times 10 to the fourth joules being given off for every 1 mole of lithium bromide that's reacting. Okay, so first thing I want you to notice, since this question said how much heat would be generated, I didn't want a sign on my answer. I just wanted the magnitude, just the number, how much heat's being given off. Secondly, this quantity, this amount of heat per mole has a specific name, and this is called the molar heat. And since this is for something dissolving, it's called the molar heat of solution because you're making a solution. The other thing I want to do here is just make sure you remember that you can convert from joules to mole or from joules to kilojoules, because more often than not, you will see values like this reported as kilojoules per mole instead of joules per mole. And so if we divide by 1,000, you're going to get 48.7 kilojoules for every 1 mole for that molar heat of solution.